Hi everyone, welcome to the webinar. My name is Clarisse. I work here at iBwave in marketing and will be your host for today. So today's webinar is the first part of the two-part webinar series on 5G, which will focus on introducing the new technology and some of its key features. So today I'm joined by Vladan Jevremovic to cover this topic. Before we get started, I just want to cover up a couple housekeeping items. So webinar will be recorded and sent to everyone after the presentation. And please feel free to ask questions to our presenter by using the GoToWebinar question box. Just as a head up, Vladan is experiencing a thunderstorm now, so it might cut off a few minutes. But if it's happened in the meantime, we will take a couple of questions from our audience with our other 5G experts, Ali. So now we're all set. Let's start. Hello, Vladan.
Hello, Clarisse. How are you?
Hello, very good. How are you?
Fine. Go ahead.
Very glad to have you here today. So first, tell us what is the biggest difference between LTE and 5G from network design and planning point of view.
Okay, so I'm going to start with what I believe was the biggest difference. There are several actually, but if I have to choose the one, then this will be it. It is frequency of operation. Before that, we did have multiple bands, obviously, throughout the world that were defined by 3GPP standards, and we had that for every technology in the past. But for this one, we actually have added a separate portion of the frequency band that is very distant in frequency from the one that we are used to seeing the system being deployed. So we have frequency range 1, which is what is also called sub 7 gigahertz range, and frequency range 2, which is millimeter wave frequency range. And I have listed here FR2 operating bands, and basically you can see them being bunched into two areas. The first area is the one close to 40 gigahertz, and it is colloquially known as 39 gigahertz band. And then there is a lower portion where the signal can go from 24 gigahertz to all the way to 29.5 gigahertz. And this is colloquially known either as 24 or 28 gigahertz, depend on whom you're talking to and in what country which band is available. And then there is sub 7 gigahertz band, and here you see a list of possible operating bands, and they are not unusual because those bands have been identified in the past by 3GPP as the bands for second, third, and fourth generation, and then also going forward future generations of digital cellular. But there was a couple of bands that have not been used very heavily in the past. And those are the ones where we are going to see quite a few sub 7 gigahertz deployments. And those are bands N77 and N78. Those are commonly known as 3.5 gigahertz bands, and they are TDD. And aside from Japan, they have not seen any cellular digital being deployed worldwide, but everything points out that this will happen, that this is where 5G will be happening in the near future. So frequency of operation, in short, is the biggest difference that I see between 5G new radio and 4G LTE.
All right, and how about beamforming? Did we have that in LTE?
Well, no, we did not really have that. And as for the beamforming, yes, it is a brand new feature, and I'm going to spend just a brief moment explaining, how it operates from the visual standpoint of view. Imagine that there is a sector in a base station, and that sector has 16 beams. And I'm using only 16, for clarity of what I'm trying to show. In reality, there will be many more beams than just 16. And we have two types of beamforming, analog and digital. In analog, we can beamform one ray at a time, or one beam at a time. And imagine that this base station has only 9 UEs, and I'm going to show you how this looks like if you beamform one at a time among 9 UEs. So this is how analog beamforming works. I'm dedicating all of my frequency to just one user at a time, and it can be quite powerful if you take into account that at millimeter wave bands you can have RF channels that are up to 400 megahertz. You can see just from the width of the channel point of view that a large bandwidth can be delivered at once to each individual user. Now, for digital beamforming, we can address several users at a time. And this is a visual how that works. The same 9 users, and I'm dedicating 3 beams at a time to 3 different users. And I'm delivering all of RF channel in each of those beams. So why do I not have co-channel interference then? Well, those beams are narrow. And yes, there will be side beams, and yes, those side beams will, give you some co-channel interference. But because we have those narrow beams, we are at least theoretically able to, ponder the thought of what happens when we do this reuse of the spectrum on a spatial manner. And this will be talked about in many more details in a few weeks when my colleague Ali Jamali will be talking about beamforming in part 2 of this series. So this is beamforming.
Okay. Can you tell us about key LTE concepts that were expanded in 5G?
Well, okay. The first one is numerology. So what is numerology? Let's start by giving you a refresher course on LTE, because LTE is a special case of 5G. And it uses OFDM, and so does, at least on downlink, 5G. An OFDM frequency time grid consists of building blocks, which is called resource blocks. And each of those resource blocks consists of subchannels. There are 12 of them in frequency domain, and OFDM symbols in time domain, and there are 14 of them. And then, so when you take into account their characteristics, which I have shown here, you see that each resource block is 100 kilohertz wide and 1 millisecond long, wide meaning in frequency. But that's not all. Each of those resource blocks consists of smaller elements called resource elements. So what is a one resource element? One resource element is one subchannel and one OFDM symbol. Okay, so it is only 15 kilohertz wide and it is only 71.35 microseconds long. And there are 168 of them inside a resource block. And this is how it looks visually. This is my LTE resource block. In frequency, I can go up to 180 kilohertz. In time domain, up to 1 millisecond. And I have 14 OFDM symbols, and as promised, I have 12 subchannels. And that's basically how a resource block visually looks like in time and space. And as I said, there are smaller elements. They're called resource elements, and there are 168 of them inside the resource block. There is also something else. It's called frame. LTE frame is 10 milliseconds long. LTE subframe is 1 millisecond long, and it is also called a slot. So the question is, how many resource blocks can we transmit in one slot? And the answer is, it depends on the channel size. At 5 megahertz, I can have 25 resource blocks per slot. At 10 megahertz, I can have 50 resource blocks per slot. Okay, but how many resource blocks per frame? Well, at 5 megahertz, it's 25 times 10, it's 250. And at 10 megahertz, it's 50 times 10, 500. So why is this resource block so important? It is important because it is the least addressable element in LTE. I can fit one customer, one UE, into one resource block. And there can be 500 of them if I do that in one LTE frame at 10 megahertz. Sure, I will have a delay of 10 milliseconds between I can address a particular UE, and the data rate will not be very high because I have only 180 kilohertz bandwidth, but I can fit quite a bit of UEs into one frame because I'm fitting one UE to one resource block. So this is how LTE frame looks at 5 megahertz channel. Time goes to 10 milliseconds, frequency goes to 5 megahertz. I have 25 resource blocks in a slot. I have 10 slots. It's 250 resource blocks in LTE frame. In LTE, those subchannels are fixed at 15 kilohertz, but in 5G, this is configurable. It can be 50, it can be 30, it can be 60, 120, 240, or even 480. And we call that SCS, subchannel size. And SCS and slot duration are inversely proportional. If SCS is larger, then slot duration is smaller. And I'm giving you examples. If I go with SCS 15, 30, 60, then slot duration will go 1 millisecond, 0.5 milliseconds, 0.25 milliseconds. And what has remained the same? It has remained the same that there is still 12 subchannels and 14 symbols in a resource block. So what has changed is slot duration and the width of that resource block. And this is example with SCS of 30 kilohertz. I have still 12 subchannels multiplied by 30, I get 360. And as we've seen on the previous slide, it is 0.5 millisecond slot, so I have 14 symbols, and now it is I have 40 symbols, and my slot is now 0.5 milliseconds. So it gets wider in frequency and shorter in time. This is another example, basically says the same. This one is 60 kilohertz. I go in frequency to 720 kilohertz, and my slot is only a quarter of millisecond long. But 5G frame is always 10 milliseconds long. So that means is if I change SCS, I will change the number of slots because each of those, the number of slots in a frame, because each of those slots gets shorter. So that's an example. I have LTE frame of 10 milliseconds for SCS being 15 kilohertz. I'm going to have 10 slots. I'm going to have 20 if SCS is 30 kilohertz, and I'm going to have 40 if SCS is 60 kilohertz. And this is summarized in this slide. All those various SCS of 15, 30, 60, 120, and so on and so forth are called numerology. Numerology 0 is SCS 15, numerology 1 is SCS 30, numerology 2 is SCS 60, and so on and so forth. So when you see numerology 2 being said about a particular configuration, you know that SCS is 60 kilohertz there. So then the question is, well, how many resource blocks do we have per slot? Well, this is a table from 3GPP, and the answer to that question is it depends on which frequency range you are at. What you will notice here that for FR1 and FR2, we do not have identical SCS combinations, and we don't have identical RF channel widths. And what you will also notice is that even though I told you that SCS can go to 240 and 480, we really have not seen yet that being defined in 3GPP. We only have seen from 15 to 120 kilohertz. And so one other thing that is obvious from here is we can do a comparison between number of resource blocks per channel between LTE and 5G if we focus on SCS of 15 kilohertz, because that is the one that is the same in both cases. For SES 15 and 10 megahertz, we know for LTE that it was 50 resource blocks for that combination. And here it is 52. So we have 2 extra resource blocks. At 20 megahertz, it used to be 100 for LTE. Now it's 106. So there are 6 extra resource blocks. So what does it mean? Why does it matter? Well, if you think about it, the more resource blocks you have, the more customers you can have, as I told you before. But more to the point, you can have a larger MADR, or maximum achievable data rate. If you can put more resource blocks into your RF channel, your data rate will be higher. The difference is not all that drastic. If you want to get technical, this 2 resource blocks, is not really all that much. It's about 4%. Here, I have 106, so the difference is about 6%. But it is one of the sources that actually raises your MADR from LTE to 5G. And then for FR2, you will notice that they don't have 15 kilohertz. They have 60 and 120 only, and that it can go all the way to 400 megahertz. But there are a few interesting things to note there, right? So if you want to take a look at what 60 kilohertz SCS will give you at 100 megahertz, the answer is it depends. In FR1, it is 135, and in FR2 is 132. So there is a little bit of difference there. Right? And then, you can compare 50 megahertz as well, and you will see that there is a slight difference there, 65 between 66. But what you will also notice that on 200 and 400 megahertz only exist at FR2, and we don't have that in FR1. And then this is illustration, finally, as to what 5G frame for 5 megahertz channel would look like. I have said at this previous slide that we would look into FR1. This is 5 megahertz, and we actually look at SCS of 30, and that is about 11 resource blocks. So I have 11 resource blocks here, and I still am using 0.5 millisecond slots. So I have 20 slots in the time domain. It must go all the way up to 10 milliseconds, which it does. So basically, I have 11 by 20 grid for 5G frame for 5 megahertz channel with SCS 30 kilohertz and at frequency FR1. So this is, in a nutshell, is what numerology is all about.
Okay, so let's take a break now and take a question from the audience. So the question is, can 5G be web-based, and now computers may act like antennas with a certain antenna plugged into USB port, for example?
Okay, well, that's an interesting question. And in theory, I don't see why not, because you could technically access your remotely your transmitter if your transmitter has IP address attached to it. However, from practical standpoint, there are several obstacles there. The first one is that you will have either laptop or desktop. If it is a desktop, your antenna will be connected to USB port that is very low to the ground, and probably, right next to several obstacles that are technically in antenna's near field. So that is not good for propagation from several aspects. If it is a laptop, then the question is it connected to AC power or not? If it is not, then it will drain your battery very quickly, that transmitter. If it is connected to AC power, then okay, your laptop is at your desk which is not quite low to the ground with the desktop, but still not good enough. You would like your antenna to be higher up. And the last and the biggest question is, how healthy is it for you to spend several hours or maybe 8 hours a day hunched over a laptop which is transmitting at, I don't know, 100 milliwatts, okay, which is typically what you will get for those DAS transmitters that are around. And I will say probably not very healthy, because even though we are at a safe distance from the transmitters, indoor transmitters, we are never quite right next to them. Okay, so that is the difference between, you know, what you do if you were next to your laptop within a foot for 8 hours a day, and, you know, being it several feet away, you know, from your desk for the same amount of time. You're much closer to it. So those are the reasons why I think, from the practical standpoint, I'll have a hard time imagining this being deployed. But as an idea, I don't see why not.
All right, thank you, Vladan. So let's go back to the presentation. Are there any features that are new to 5G but have its roots in LTE and LTE-A?
Yes, there are. So there is a bandwidth partitioning, and this is kind of a little bit backwards of what we have already done in LTE-A. In LTE-A, we were connecting disjoint spectrum, non-continuous RF channels to act like one. And here what we do is we are actually splitting an existing RF channel into smaller portions. And those smaller portions will have different characteristics, which means they will have their own numerology. And so why we want to do that? We do that because we want to segregate users by their requirements, which is high or low latency, high or low data rate, high or low user density, and so on and so forth. So this is an example of that. I have a 20 megahertz FDD channel, so I'm showing you what happens here. In a downlink channel, I have separated this 20 megahertz into 3 bandwidth parts, 0, 1, and 2. And the specification that you do for bandwidth parts are by the number of resource blocks, not necessarily by frequency. You don't say, I want 5 megahertz. No, you say, I want 10, 20, or 30, or 40 resource blocks. And then you calculate what frequency chunk you will get by that number. So here I have specified 40 resource blocks for mu0, 10 resource blocks for mu1, and 10 for mu2. And you will see that even though I have the same number of resource blocks for mu1 and 2, I have different bandwidth. Why? Because resource blocks are not the same size. The one for mu1 is 360 kilohertz, and for mu2 is 720 kilohertz. And likewise, you see that I have the same bandwidth for mu0 and mu2, which is 7.2 megahertz, but I have different number of resource blocks. And the answer is, again, RBs are not the same size. This one is 180 kilohertz, mu0, and this one, mu2, is, like I said, 760. So that's why we see that difference. Then there is something called slot formatting. This is basically what we have had in LTE for TDD channels. We had some flexibility when it came to figuring out how many slots we want for downlink and how many for uplink. And I think there was a total of maybe 8 or 9 possible combinations. And you would choose a combination and that would be it. You will have so many downlink slots in, and then there would be a buffer, and then there would be uplink slots, and then maybe again a buffer. And that was that. You choose one combination and this is it for you. Here we have many more possible combinations, okay? We have many more options. And the operator should define, first of all, the periodicity of transmission. It can go from 0.5 millisecond up to 10 millisecond. Then the number of consecutive downlink and uplink slots within that periodicity. Then the number of consecutive downlink and uplink symbols within that buffer slot that exists between downlink and uplink. And there is only one buffer slot now. We used to have a possibility to have a buffer slot every time when the transmission changes direction. Right now, there is only one buffer slot, and that is between downlink transmission and uplink transmission. And then also, an operator has to define a number of guard symbols within that buffer that separates downlink and uplink symbols. And this sounds complicated enough, but if we look into this example, we'll see that it is not quite that bad. We see 6 downlink slots, and then we see some downlink symbols within this buffer slot. And then we see some uplink symbols within the same buffer slot, and we see some empty symbols or guard symbols. And then there are uplink slots, and periodicity is 5 milliseconds. So what happens once those 5 milliseconds are gone? Well, we have downlink being transmitted again without a buffer. The buffer does not exist between uplink and downlink, only between downlink and uplink. So how do we go about figuring out how many slots we want for downlink, how many for uplink, how many guard symbols, and so on and so forth? Well, there is this big and scary looking table at 3GPP 38213. But I will walk you through it, and you will see that it is not quite that bad. There are 55 possible, well, 56 because format goes from 0 to 55. So there are 56 possible combinations, and they all specify what is happening in each of those 14 symbols in a slot. So I'm basically now being able to address what is going on per symbol, which I was not able to do in LT. So that is evolution from the previous standard. So format 0 is interesting, and so is format 1. All of them, all of the symbols in a slot are downlink, or all of them are uplink. So format 0 is all downlink. So what happens is basically I need to define my my formatting of the slots for a periodicity on a per slot basis. What it really means is that I will tell the system that this slot is format 0, this one is format 0, this one is format 0, this one is format 0, format 0, format 0. Okay. Then I will say for those 3 that they are format 1 because they're all uplink. And then what happens with this one? I want 3 symbols to be downlink, and I want 3 symbols to be uplink, and I want 8 to be empty. So if you look at the format number 27, the first 3 are downlink, the last 3 are uplink, and everything else is F. What is F? It means flexible. It also means it could be just guard spot, just a silent symbol. And that's what it is. So basically what you are doing is you go off and you are formatting on a slot basis, and then you say 0, 0, 0, 0, and then you say something like 27, and then you go 1, 1, 1. And that's how you would format this particular periodicity of transmission that lasts 5 milliseconds. So that answers your question, Clarice.
All right, thank you, very interesting. So let's take another question from the audience. The question is, what will a 5G implementation look like insofar as differences from the current 4G in-building designs?
Well, I see the difference being in the fact that we are going to see deployment of at millimeter wave frequencies and in selected venues. selected class of venues, I should say. And those would be the venues when we have a lot of UEs, the high density of users. Some would say extremely high density of users, like stadiums and convention centers. But those venues also have mostly line of sight. So millimeter wave does not really propagate all that well through walls. Some walls, you can get the first wall through, but those heavier walls, you will not get anything through. So to be on the safe side, line of sight with most customers, most of the time, is required, and you have that in stadiums, and you have that in convention centers, and I see that perhaps down the road we will also use this for hotspots, and hotspots like in coffee shops. We can totally do that because you have customers that are nearby, and you can have a line of sight, and they sit down and they browse, and they need lots of bandwidth, and you can give it to them with the millimeter wave band, because there you can go up to 400 megahertz. So that is, what I see as a difference between 5G and LTE. We will have millimeter wave, and then that millimeter wave is going to work well in a certain class of venues with a very high density of users.
Okay, yeah, thank you, Vladan. Let's talk about reference signals. So we used to have cell reference signals in LTE. Do we still have that in 5G?
Well, yes. LTE has a single cell reference signal, which is RSRP. And 5G does not have a cell-specific reference signal, like cell reference RSRP. So the question is why? Well, it's to reduce the overhead. What we have here, I have given you again, LTE and what it can do, and those marine blue slots are your reference signal, or RSRP, in LTE. And you can see them in 4 different OFDM symbols. And in each of those OFDM symbols, you know that there is 14 of them, and then you can see 6 being assigned to RSRP. So, if we make this a little bit more flexible and not mandatory and rigid like this, then maybe we will reduce the overhead. And when we reduce the overhead, then, the maximum achievable data rate goes up. So, what do we have in 5G? As I said, 5G NR does not have cell reference signal, but has reference signal specific for other signals. So there is this demodulation reference signal, or DMRS, and it is used as reference for 3 types of signal. PDSCH, which is a signal used to carry data. PDCCH is a control channel, and PBCH is broadcast channel. And then there are 2 more. There is a channel state information reference signal, which is CSIRS, used for channel state information. And there is phase tracking reference signal, PTRS, used for phase tracking. And they are all flexible. What it means is there is a lots of parameters to configure. So you have to spend more time upfront configuring your system to get the custom settings that you like. But the benefit of it is that you may come out ahead of what was before with LTE. So DMRS is specified by 4 entries. There is a maximum signal length, which is 2 options. Configuration type, also 2 options. PDSCH mapping type, also 2 options. And DL DMRS add position, 4 options. That's a total of 32 options that you need to set that affect the number of location of DMRS. Visually, how does it look like? Well, I can't really show you how that looks in a time and frequency domain because there will be 32 options for that. So I can show you what those options are. For maximum single symbol length, it can be single or double. For configuration type, it could be type 1 or type 2. For PDSEH mapping type, type A or type B. And DLDRMS add position could be 0, 1, 2, and 3. Well, I didn't tell you much, right? Well, this is how it is defined in 3GPP standard. I have basically figured out how to calculate the total number of those DMRS signals based on those configurations. And it is described in detail in 3GPP. And I have listed, what they are, but I really don't have enough time for this presentation to go into details what type A and type B is and how DLDRMS add position of 2 affects the total number of those DMRS signals. But it does, and depending on those, you can have more or less DMRS in your frame, which means that your data rate will be lower if there are more of them and higher if there are fewer of them. PTRS also has plenty of options. There are 3 entries. First one is time density of PTRS, 3 options. The second parameter is DLPTRS add position, which is 2 options, and frequency density. There are 4 options. So there is a total of 24 combinations that you can have out of those 3, and they all, in fact, have a different number and location of where those PTRS are. Different number of PTRS in a frame and different locations in a frame where PTRS are. So I keep saying number and location. Why is that important? Well, I told you already why number is important, because you would like to have fewer of those reference signals to have higher maximum achievable data rate. But why is location important? Location is important because you have to specify transmit power for all of the signals in 5G, including PTRS and DMRS and all others. And once you do that, then you have to go through each and every symbol in your resource block to see if the power adds up to be equal or less than the total available power at the amplifier that you have in your sector, or at your transmitter, indoor transmitter. So you have to do a power check, and to do a power check, you have to know exactly, what is going on in each of those symbols that are transmitting one at a time. And that's why you need to know where the PTRS is, what DMRS is, and so on and so forth. You will be specifying their power, and you want to make sure that you are not exceeding allocating power for your power amplifier. And then this is how it looks visually. This time you only have numbers, don't have the phrases. The time density of PTRS is either 1, 2, and 4. The DLDMRS at position is either 0, 1, 2, or 3. And then there is a frequency density of either 2 or 4. And then there is the most complex of them all. It's CSIRS. And CSIRS is the reference signal for channel state information. It's transmitted in the same OFDM symbol as PDSEH. And it measures radio channel quality and reports back to E node B. High CSI means that high modulation order is possible, and that gives us high maximum achievable data rate. And as per 3GPP TS 32.12.11, in a specific section 7.4.1.5, CSIRS is defined by periodicity, the number of resource blocks carrying CSIRS, and CSIRS density and CDM type. Now this one gets a bit messy, and I invite you all to go to that 3GPP document to take a look at how is that all defined. So I didn't really put any visualization for that, because some of this is not even the option. For example, the second one is, yes, it will depend on the number of RBs carrying CSIRS, but that really is not user definable. This number has to be divisible by 4. So if you are into 20 megahertz band and you have SCS of 15 kilohertz, you might remember that I said earlier that there are 106 resource blocks there. So 160 is not divisible by 4, but 104 is. So the program will automatically figure out that the number of RBs carrying CSIRS is not 106 but 104. So you basically go from, then if that number that is maximum is not divisible by 4, you go one lower than that, and then you use that. And if you are at SCS 15 and you have 10 megahertz channel, then you will have 52 RBs, and then you divide 52 by 4. Well, it can't go, but 50 can. So then, okay, you say 50 RBs will be carrying CSIRS. But anyway, this is CSIRS, and that's the last one. And for it, you pretty much also have to figure out where they are and how many of them they are. So that is your reference signal for 5G.
All right, Vladan. So now let's take another question from the audience. So this question is, do you consider 5G a disruptive or evolutionary technology? And does current 4G phone work on 5G network?
No, the 4G phone will not work on 5G network. And the 5G is evolutionary because it is evolution of the standard that we had, LTE standard. So 5G is really what we had for LTE, but more, I would say, more flexible with more options, more bells and whistles, if you will. So I don't consider that a disruptive technology. I consider this as evolutionary technology.
All right, interesting. So Vladan, I seem to remember that we also had synchronization signals and control channels in LTE. So did their configuration also change in 5G?
Well, yeah, synchronization signals and PBCH, they make an SS block, okay? And then so that SS block is basically the one that is not flexible. I mean, everything else is flexible, but this one is not. It is going to be over 4 symbols in time domain and over 20 resource blocks in frequency domain. Obviously, as resource blocks, will change, the duration, the width of resource blocks, will be different. The duration of OFDM symbols will be different, but always you will have this size of synchronization signal block. And inside we have a primary and secondary synchronization signal. SS block is the only signal that is always transmitted. And it has operator defined repetition time. So this is operator configurable. Each eNode beam can have its own synchronization block transmission slot, which is different from other beams. My colleague Ali Jamali will talk about this more when he talks about beamforming. But basically, that SS block is transmitted over SS beams, and you basically, each SS beam will have a different transmission slot for this SS block. And then your phone is going to measure those beams and measure the delay of those slots. And if he measures that delay is the strongest, for example, delay number 5 is the strongest, then it will say, all right, so I am the closest to SS beam number 5, or I'm in coverage of SS beam number 5, and that's how it basically tells other beams to PDSCH beams to send payload in that direction. That's how you basically figure out which beams need to address which UE. Basically, SS block is used to scanning the field, and UEs can read those delays and can report back, and then the system can say, I know where UE is. The UE is in the area where SS beam number 5 has coverage, so I'm going to point my PDSCH beams in that direction as well. So that's why this is valuable. And this is all done in real time for each UE. Now, the options for SS synchronization signals are number of SS or PBCH block repetition. It can go from 5 to 60. I mentioned that already, and this is operator configurable. Excuse me. And then we have also the SS PBCH block case. Can be A, B, C.
Oh, I think we lost Vladan. Hello. Oh, sorry for that. So we're going to take a question from the audience. Vladan should experience some troubles connecting. So we're going to take a question for Ali, our other 5G expert. So I have a question for you, Ali. Will 5G be deployed in all other existing spectrum frequency bands? Will it degrade data speeds to the preceding fourth generation? And how long is 5G predicted to rule the industry?
Well, with respect to the frequency band, as Vladan presented at the beginning, there are two different bands defined. So for the sub-6 or sub-7 gigahertz band, so they're almost the same band used for fourth generation. So it will be almost the same bands except the 3.5 gigahertz band. So, but for the frequency range 2, so it is almost new frequency band defined for the millimeter wave bands. So that's the question regarding the frequency band. And then how long is 5G predicted to rule the industry? I think we are in the phase now of starting the deployment of this 5G new radio technology. So we are starting seeing some deployment and some implementation of this new radio technology.
Okay. Thanks, Ali. So maybe we will take this time waiting for Vladan to answer some of your live questions
maybe
too.
We can take some questions.
Yeah. So I'll leave you, Ali, to choose a question.
We have here another question. Do we have FDD in 5G? And the answer is yes. So almost the frequency bands in sub-6 or sub-7 gigahertz, they are defined in FDD or TDD. Only the frequency range 2, which is in the millimeter wave, they are defined only for TDD deployment.
All right, thank you, Ali.
Let's see here if we have. Yes, do we call it sub-7 instead of sub-6? So this is mainly related to the new regarding to the releases of the 3GPP. So the latest release, there are new defined bands which are close to the 7 gigahertz, and that's why we should call it sub-7 gigahertz instead of 6. So it is only a question of updating all these frequency bands with respect to the 3GPP documents.
Okay, thank you. Interesting, Ali. So we're still waiting for Vladan. Sorry for this interruption. Is there another question we could take?
One question is, what are resource blocks? So the resource block, as in LTE, are defined with respect in the frequency domain. So one resource block is 12 resource element, and it is exactly as defined in the LTE. The only difference here is the resource block in 5G, the size of this resource block, because we have different subcarrier spacing and different definition for each one. So that means the resource block, the size of resource block would be different from one subcarrier spacing to another. In LTE, it was fixed to 12, and one resource element was 15 kilohertz. So one resource block would be in 4G 180 kilohertz, but for 5G, because we have different subcarrier spacing, so some resource block will have more than 180 kilohertz. So it will depend on the definition of your subcarrier spacing.
Okay, thank you for that, Ali.
Okay, let's see. Can we use deep learning technique to improve 5G technology? This is a very large team of research in the area of 5G, but I think this is something that my opinion is that it is something that can happen. And yes, there are a lot of research ongoing on deep learning. And yes, I believe that this is something that can be used in 5G.
Okay, thank you. So I think Vladan is back. Can you hear us, Vladan?
Yes, I can. I am now going to continue. Just let me know if you see my screen.
Yeah, we can see your screen.
Okay.
So I think we were at slide 32 exact.
33. Okay. Well, yeah, I told you about SS options, and then yeah, core set. Did I say anything about core set? Did you hear that, or did I not cover it?
No, we didn't hear that. So I think we were just right.
So anyway, there is one more of those 5G signals. It's called core set, and this is a new name for control channels, PDCCH. And LT PDCCH would occupy 1 to 3 symbols over the whole RF channel, and PDSCH signal could not be transmitted over those symbols, which was a bit inconvenient. And in 5G, they have remedied that. Core set is transmitted over a smaller portion of the channel, and other signals, such as PDSCH, can be transmitted in the same symbols where PDCCH is transmitted, which is good because it reduces the overhead and increases the MADR. And then, so this is how the core set parameters look like. We have, they're called RE groups or reg. One reg has 12 resource elements, and minimum 6 regs have to be defined. And this is how it looks into bandwidth part. So this is a portion that of OFDM symbols where core set is transmitted. And so there is this part right here when they are not, and it's the same symbols. So there I can transmit PDSCH. And so I'm not wasting, all of the symbols for control channels. So that is the end of that presentation where we talk about, what we had for signals in 5G with respect to how it was in LT.
Okay, thank you. Vladan, we haven't talked about 5G signals. So which signals are going to be key parameters for network coverage design and planning? Right,
so there is a document in LT that basically talks about which signals you should measure and report back. And in LT at the beginning, we had only 3 measured KPIs, and it was RSRP, RSRQ, and RSSANR, and it is for to cell reference signal. At the beginning. Later on, we had more, but this is the beginning. Okay, so it's fair to compare beginning of LT with beginning of 5G. Now we have 6. Why? Because we are dealing with synchronization signals and channel state information signal. So both SS and CSI have 3 measurable KPIs each, which is SSR SRP, which is for their reference signal, SSR SRQ, which is basically the same type. I will say in a few moments, what of these are, but the definition is given in 38.215 for all 6 of them. So I'm going to briefly go through it. So SSR SRP is received power per resource element, and SSR SRQ is n times SSR SRP divided by RSSI, where RSSI is total power in the whole RF channel or bandwidth part. N is the number of resource blocks in RF channel or bandwidth part. And SSSANR is the ratio of serving versus non-serving SSRE with added thermal noise. So basically I'm measuring various aspects of my synchronization signal. Why synchronization signal? Because, as I said, SS block is the only one that will be transmitted all the time, regardless of whether you have customers. So you can say in a way that SS is sort of, doing the business of the transmitting pilot signals, if you will, like we had it for LTE or even for WCDMA. So you can say that that is what SS does. Then the same thing is for CSI. It really is about the same types of definitions. For SS, I'm not going to go and repeat that. It's virtually the same. You can go and read in the document, what the definitions are. There may be some subtle differences, but regarding to which port, antenna port, you want to measure this. But I will leave that to a reader to discover. And with that, I am closing down my presentations and opening to questions.
Thank you very much, Vladan, for this great presentation. We already covered some questions with Ali, but I have one question for you from the audience. So the question I have is, what is the main purpose, benefit of having configurable carrier spacing and number of slots per frame in 5G? And is it for different user traffic profiles like IoT, heavy downloaders, etc.?
Yeah, I touched on that subject a little bit there when I said you can have, requests for very fast, exchange of information, or maybe delay is acceptable, or you can have a request for very high bandwidth. Sometimes, long bandwidth is okay, and so on and so forth. So yes, that is why you want to have different bandwidth parts. So you have a different user profile, so you can address those users in the same RF channel. So you can say this portion is for those that want very high throughput. This portion is for those that need many connections in small areas like IoT, and the third one are yet for something different, that is going to maybe connected car that really does not tolerate much of a delay. So yes, basically you want to address your different class of users in the same RF channel and keep them together. That is why you have different numerology.
Okay, thank you very much. I think that's a wrap. So thank you very much, Vladan, for this great presentation. And thank you, attendees, for joining us on today's webinar. And I hope to see you at the part 2 of this webinar series on 5G.
Thank you very much, Clarice, and everybody have a good afternoon or evening, wherever you may be. Thank you.
Thank you. Bye-bye.